For number 3, we're going to apply what we learned about matrix exponentials to find the general solution to y prime equals ay, for a equals negative 1, 0, 0, 2, negative 5, negative 1, and 0, 4, negative 1. So we know our solutions will take the form e to the ta times v, where e to the ta equals e to the lambda t times e to the a minus lambda I t times v. So now we just have to find out what lambda and v are, our eigenvalues, and what this matrix exponential equals. So let's start off with a minus lambda I. That's going to equal negative 1 minus lambda, 2, 0, and 0, negative 5 minus lambda, 4, and 0, negative 1, negative 1 minus lambda. If we find the determinant of this and go through some algebra, we'll end up with negative lambda plus 1 times lambda plus 3 squared. So this gives us, when we set this equal to 0, this gives us 3 eigenvalues of the matrix. Gives us negative 1, negative 3, and negative 3. So we have one eigenvalue with a repeat, with algebraic multiplicity 1. And then we have negative 3, which has an algebraic multiplicity 2. So we're going to use this matrix exponential to cover both of these. So we'll start with our algebraic multiplicity 1. So we know our solution 1, y1 will equal e to the ta times v1, where v1 is going to be our associated eigenvector. So e to the ta is going to equal e to the lambda 1t times e to the a minus lambda 1I times t times v1. So lambda 1 in this case is going to be negative 1. So this is going to be e to the negative t times e to the a plus I times t times v1. So now we're going to find out what v1 is. Since this is algebraic multiplicity 1, we know that if we look at a plus I, which is 0, 0, 0, 2, negative 4, negative 1, and 0, 4, 0, and we look at the null space of this, we're going to find our eigenvector. So v1, we're going to say this equals a, b, c, and we want to find v1 such that a plus I times v1 equals 0. We've done this before, and I'm just going to give you the result. v1 equals 1, 0, 2. So this gives us that y1 equals e to the negative t times e to the a plus I t times 1, 0, 2. So now we got to find out what this quantity is. We expand out this matrix exponential times the vector, and you know what, I'm going to leave this as v1 for now. This is going to give us v1 plus t times a plus I v2 and t squared over 2 factorial times a plus I squared, and so on. So, and sorry, this should be v1. There should be a v1 here as well. So we know that v1 is in the null space of a plus I, so this is going to go to 0, and everything else beyond it will go to 0. So we're left with e to the negative t times v1, which is just e to the negative t times 1, 0, 2. So we can, this is what we've been doing, and this is exactly the same solution we would have got if we had done this using our old methods. So now we can go focus on our eigenvalue with algebraic multiplicity 2. So now we know our two solutions that we have left over, y1 or y2 and y3 will take this form, e to the ta times v2 and e to the ta times v3, where v2 and v3 are going to be a generalized eigenvector. Expanding this out, this gives us e to the lambda t times e to the, and this is our second eigenvalue, so we'll say lambda 2 times e to the a minus lambda 2 I times t times v2, and this will be e to the lambda 2t times e to the a minus lambda 2i t times v3, and plugging in lambda 2, which is negative 3, we get e to the negative 3t times e to the a plus 3i t times v2, and then e to the negative 3t times e to the a plus 3i t times v3. So now we're going to have to expand this matrix exponential out. And let's start by looking at a plus 3i. So a plus 3i equals 2, 0, 0, 2, negative 2, negative 1, 0, 4, 2. And if we row reduce this to look at its null space, we get 1, 0, 0, 0, 2, 1, and 0, 0, 0. So this null space will have a dimension of 1. And we want to find a power of a plus 3i, so the null space dimension equals our algebraic multiplicity, which is 2. So we need to find a plus 3i squared. And that's going to equal 4, 0, 0, 0, 0, 0, and 0, 0, 0. Or, sorry, 8, 0, 0. And row reducing this, we get 1, 0, 0, 0, 0, 0, 0, 0, 0. That has two free variables, or the null space does. So our null space has dimension 2. So now we want to find the generalized eigenvectors associated with this. So we say that v, 2, and 3, say this equals def. And we want to find v2 and 3 such that a plus 3i squared times v2 and 3 equals 0. So this gives us this augmented matrix. Row reducing it, again we get 1, 0, 0. So that just tells us that our first component, d, equals 0, but e and f are free variables. So v2 and 3 equals 0, e and f, or 0, 1, 0 times e plus 0, 0, 1 times f. So this gives us our v2 and v3. v2 is 0, 1, 0, which we get from here, and v3 is 0, 0, 1. So now we can look at y2, which equals e to the negative 3t times e to the a plus 3i t times v2. So let's expand this out. This is going to be v2 plus a plus 3it v2 plus a plus 3i. And we should have a t squared over 2 here. Times v2, and so on. But we know v2 is in the null space of a plus 3i. So this will go to 0, and everything else beyond it goes to 0. So our solution is e to the negative 3t times v2, which is 0, 0, 1, plus a plus 3i, which is 2, 0, 0, 2, -2, -1, and 0, 4, 2. This is all times t, which I should have put in the front, but it's here, so it doesn't really matter. Times 0, 0, and sorry, v2 is 0, 1, 0. So v2 is equal to 0, 1, 0 times t plus 0, -2, 4. That gives us a solution of e to the -3t times 0, 1 minus 2t, and 4t. Now to find y3, we take, do the same thing, so e to the -3t times e to the a plus 3i times t times v3 now, and that's going to be e to the -3t times v3 plus t a plus 3i v3 plus t squared over 2 factorial times a plus 3i squared v3. But we know that v3 is in the null space of a plus 3i. This will go to 0, and everything beyond will go to 0, so we're going to be left with e to the -3t times v3 plus t times a plus 3i v3. So this is going to equal e to the -3t times 0, 0, 1 plus t times a plus 3i, which is 2, 2, 0, 0, -2, 4, and 0, -1, 2 times v3, which is 0, 0, 1. And if you simplify this, if you multiply 0, 0, 1 by that matrix, you get 0, 0, 1 plus t times 0, -1, 2. And this gives us y3 of e to the 3t times 0, -t, and 1 plus 2t. So our total solution, y of t, which is c1 times y1 plus c2 y2 plus c3 y3, where c1, c2, and c3 are arbitrary constants. This is going to be c1 times e to the -t times 102 plus c2 times e to the -3t times 0, 1 minus 2t, and 4t, and c3 times e to the -3t times 0, -t, 1 plus 2t. This is our total solution. We can check to make sure that y1, y2, and y3 are independent by looking at the fundamental matrix evaluated at time 0. So that's going to be y1 of 0, y2 of 0, and y3 of 0. So this is the matrix 1, 0, 2, 0, 1, 0, and 0, 0, 1. And we check the determinant of this. And the determinant is going to be 1 times the determinant of 1, 0, 0, 1, and that's going to equal 1. And this is not equal to 0, so that means that 3 solutions are linearly independent. So this is the general solution. For number 4, we want to find the general solution to y1 prime equals 6y1 minus 4y3 y2 prime equals negative 2y1 plus 4y2 plus 5y3, and y3 prime equals y1 plus 2y3. So we got to convert this into a matrix equation first, and we can do that really quick by making this a vector, y1 prime, y2 prime, y3 prime, which we can say just equals y1, y2, y3 primed, which is just the vector y primed. And this is going to equal on this side 6y1 plus 0y2 minus 4y3, negative 2y1 plus 4y2 plus 5y3, and 1y1 plus 0y2 plus 2y3. And this is going to equal the matrix 6, 0, negative 4, negative 2, 4, 5, and 1, 0, 2 times y1, y2, y3. So if we define the matrix A to be that matrix we just had, then this turns into the equation y prime equals a y. If we define this to be the vector y. So now that we have this in this form, we can go and start finding the eigenvalues. We look at the matrix A minus lambda I, that is 6 minus lambda, negative 2, 1, 0, 4 minus lambda, 0, and negative 4, 5, 2. The determinant of this, if we expand along this direction, is going to be 0 times the determinant of its associated submatrix. Doesn't really matter what that is because it's times 0. This is going to be negative, and then plus 4 minus lambda times its associated submatrix, which is 6 minus lambda, 1, negative 4, and 2 minus lambda. Sorry, this should be minus lambda here. And we also have another 0. This should be a minus 0 times the determinant of its associated submatrix, but it doesn't matter what that is because both of these go to 0. So we're left with the determinant of a minus lambda I equals negative lambda minus 4 times 6 minus lambda times 2 minus lambda plus 4, and this will end up being negative lambda minus 4 cubed. So if we set the determinant equal to 0, this gives us lambda equals 4 as all three of our eigenvalues. So algebraic multiplicity equals 3. So now we know y1, y2, and y3 will take this form, e to the ta times v1, e to the ta times v2, and e to the ta times v3, where v1, v2, and v3 are all generalized eigenvectors. So if we write these out in a different form, this is going to be e to the lambda t times e to the a minus lambda I t times v1. It's going to be e to the lambda t times e to the a minus lambda I t v2. This is going to be e to the lambda t times e to the a minus lambda I t v3. And our next step is just to plug in the eigenvalue. It's the same for all, so it's e to the 4t, e to the a minus 4i t v1, and then so on for the others. So now we just had to find out what V1, V2, and V3 are. And V1, V2, and V3 are going to be associated with some certain null space of a power of a minus 4i by the Cayley-Hamilton theorem. So by the Cayley-Hamilton theorem, we know that the matrix A must satisfy its characteristic polynomial, so a minus 4i to the third times a negative, if you want, has to equal 0. Or in other words, a minus 4i to the third equals 0. So that means that this equals this matrix, which has every vector in its null space. So null space of this is going to equal all of R3. So that means we can choose any vector ABC to be in this null space. It's going to be A times 1, 0, 0 plus B times 0, 1, 0 plus C times 0, 0, 1. So that means our V1, we can just make these equal to the standard basis vectors. V1 is 1, 0, 0, V2 is 0, 1, 0, and V3 is 0, 0, 1. So that means that we can write Y1 as e to the 4t times e to the a minus 4i t times V1, and that's going to equal e to the 4t times V1 plus t a minus 4i V1 plus t squared over 2 factorial a minus 4i V1. And everything beyond that's going to go to 0. So our solution then is and this should be squared, sorry. So we need to find out what a minus 4i and a minus 4i squared are. So to do that, let's just look at a minus 4i. That is 2, 0, negative 4, negative 2, 0, 5, and 1, 0, negative 2. And if you square that, I'll let you check the work, but that will lead to 0, 0, 0, 1, 0, negative 2, and 0, 0, 0. So now using that, we can plug that into our solution. And this will give us a y1, and once you simplify everything, of e to the 4t times 1 plus 2t, negative 2t plus t squared over 2, and t. And likewise for y2, it's going to be e to the 4t times e to the a minus 4i t times v2, and that's going to equal v2 plus t a minus 4i v2 plus t squared over 2 a minus 4i squared v2. And I'll let you do the calculations for that, but that's actually just going to turn out to be e to the 4t times 0, 1, 0. And for y3, do the same thing, e to the 4t times e to the a minus 4i t times v3. It's going to be v3 plus t a minus 4i v3 plus t squared over 2 a minus 4I squared v3. And I'm not going to do the calculation again, but that's e to the 4t times negative 4t, 5t minus t squared, and 1 minus 2t. So combining all these, our general solution is going to be c1 times e to the 4t, 1 plus 2t, negative 2t plus t squared over 2, and t, plus c2 e to the 4t, 0, 1, 0, plus c3 e to the 4t times negative 4t, 5t minus t squared, and 1 minus 2t. So if we split this up into what y1 is just going to be c1, and we can factor out e to the 4t actually. So e to the 4t times c1, 1 plus 2t, plus c, or minus c3, minus 4c3t, and y2 is going to be e to the 4t times c1 negative 2t plus t squared over 2, plus c2 plus c3 5t minus t squared, and then y3 is going to equal e to the 4t times c1t plus c3 1 minus 2t. And these are our solutions.